Our first speaker is Heiko van der Mosel, who will speak on integral Menger curvatures.
Thanks, Jason. Thanks very much for the invitation. It's great to be here. Is the microphone working well? Okay. So I would like to give an elementary survey of what we do with Menger curvatures from the point of view of mathematical analysis. Let's start very simply with a closed curve gamma in R3, so in Euclidean 3 space. Whenever I write gamma, I mean either the image that you see of the curve or the nicest possible parameterization, which is the unit speed parameterization, or so-called arc length parameterization. So we all know that if you take a point z on that curve, then you can associate to that point the local curvature, kappa of z. And a geometric way of describing that is you take the best approximation of the curve locally near z by circles. And this will give you the so-called osculating circle with radius little r of z. And this radius is the inverse of the local curvature. And I want to emphasize here that this local curvature function just takes one point and then gives you the value of curvature. So it's a function depending on single points. Likewise for surfaces. Let's say two-dimensional smooth surfaces in R3. So for instance, this cylindrical surface sigma here with a point P on it. How do we get local curvature there? Well, one way of getting that is you intersect the surface with so-called normal planes. These are planes through P that are normal to the tangent plane of the surface at P. And since this is always a transversal intersection, we get nice intersection lines, again curves that possess a local curvature at the point P. Since we have many, many such normal planes, you have many, many such curvatures, which we call normal curvature, kappa nor, ranging in this example between 0 and 1. And you take the minimum and maximum value of these normal curvatures and call them principal curvatures. So we have two principal curvatures, and from them you can build the classic mean curvature function h at the point P as the arithmetic mean of these principal curvatures, or if you want the Gauss curvature as the product of these principal curvatures. And again, I emphasize, these curvature functions depend on single surface points. In contrast to that, it was in the 1930s that the Austrian mathematician Carl Menger introduced or investigated functions that depend on more than one point on the curve. So for instance, the circumcircle radius r of x, y, and z, where x, y, and z are curve points, this gives you a function that I call multi-point function because it depends on various points on the curve. So Menger had he knew two basic things. The first thing was, well, if you have a smooth curve, and let's assume that for a moment, and you take the coalescent limit of x going to z and y going to z, then you find that this radius tends to the local radius of curvature at the point z again. So the inverse tends to local curvature. In that sense, for smooth object, this multi-point function is able to capture local properties. Menger also knew that there is an elementary formula for this function capital R of x, y, z just in terms of mutual distances between the points. So he was interested in deriving a purely metric geometry, just depending on distances, in contrast to classic differential geometry. So we don't follow that thread here, but I want to add a third observation, which is also very simple. To define this R of x, y, z, you don't need any smoothness of the curve. You actually don't need the curve. Some people say that this quotient alone is called the Menger curvature of the 3 points. And I want to stress this point because my background is the calculus of variation, where you very often have to minimize energies. And very often you can't minimize these energies if you stay within classical function spaces or classical geometric objects with high degree of smoothness. You have to enlarge that space. So for instance, the term Sobolev spaces was mentioned on Monday. The Sobolev spaces were basically invented to have a larger function space to find minima of certain variational problems. And then later on, when you have a minimum in this non-smooth class, you can try to prove that this minimum actually is better, is again a classic function or a classic geometric object. So this in mind, and motivated by completely different issues, Gonzalez and Maddox reconsidered in 1999 this multipoint function again. But now they were looking for the smallest circumcircle radius that you can get when all these 3 points are allowed to vary along the curve. So they were looking for the smallest circumradii. This might lead you to a limiting circle like this here, where you somehow capture the fact that the local curvature at that point is very high. There's the highest local curvature for this curve. But you also may end up with this completely different circle, like this one here, in the middle, and the radius of that circle has nothing to do with local curvature at this or this point. It rather captures the fact that there are two strands of the curve coming close to each other in space. So, turn that around. Let me call that minimal circumcircle radius delta of gamma. If you have a certain control of delta from below, saying that you know that this is positive, strictly positive, then you might control local curvature effects as well as these global effects. And this interplay of local and global effects is reflected in the following basic theorem, proved independently by Jason, Rob, and John, and also Gonzalez, Maddox, Zurich, and myself some 10 years ago. It says the following: positive delta here, or as I prefer to write it, 1 over delta being finite, because I interpret this as a geometric form of an energy, is equivalent to saying that a non-smooth curve actually is much better than initially, and also embedded. So when I say much better, the C11 means that we have a continuously differentiable curve, and a priori you just put in a continuous, better to say a Lipschitz continuous curve, so a non-smooth object. You get a continuously differentiable curve, and the tangent vector is also nicely continuous, also Lipschitz continuous. This is the meaning of the second one here. You can just imagine this being almost C2, so almost twice differentiable. But you have curvature almost everywhere, at almost every point, and this curvature is actually bounded by exactly that quotient here. So you have nice control, and a more geometric way of expressing that basic theorem is the following. You can, if you have delta being positive, you can call that thickness. That's what Gonzalez-Maddox did, because you can assign to each curve a tubular neighborhood of exactly the radius delta, which becomes to be regular, because it consists of normal disks of radius delta that do not intersect each other. So it's a very nice regular tubular neighborhood where you have a unique next point projection back onto the curve, and if you increase that radius slightly, you immediately come to singularities of this tube radius here, because local curvature is high. And if you increase the radius here of the tube, you would have self-intersections of the tube because of this global interaction between the two strands. And this is a good and very valid excluded volume constraint. And this is the heart of all the analytic results concerning curves with a positive thickness. And I will give you some applications. And I will only just briefly mention the application of ideal knots, because there will be several talks on this, on ideal knots and links later on. Just let me say that this object is a minimizer of so-called rope length, which is the quotient of length and thickness. And one way of obtaining these things just visually is to let some algorithm run. This is not the ridge runner. It's probably not as reliable as the ridge runner, but to have a vision of what happens when a knot pulls tight is this little movie here. And I will just defer that information on ideal knots and the more actual work on that to later talks. I would like to point out that you can also work with elastic rods, minimizing elastic energies, with the prescribed minimal thickness of the rod. So you can speak of wires, and you can also look at nice packing problems. And I would like to introduce you to one packing problem which is probably not that well known in this community. It is the search for the longest rope on the unit sphere. So this is a mathematically idealized packing problem, but it has a nice outcome. It's not any sensible to look for the longest curves on the unit sphere, because you can enlarge the length by just inserting wiggly parts to make the length of a curve arbitrarily long. But to minimize the length function L on the set of curves that have a minimal thickness, so carry around a tube, this makes sense, because if the tube is too long, you pack the sphere, you overpack the sphere. And this is a problem that Henry Geller came up when he was investigating ideal knots on the S3, so the three-dimensional sphere on R4. And this is what turned out to be a nice toy problem for that, because we actually know for many, many given minimal thickness values the exact solution set. So existence for all reasonable thicknesses is no big deal. You say, well, should exist, and this works fine. But for an infinite sequence of given minimal thicknesses, we find exactly the solution. We can construct the solutions explicitly and can prove that they are unique up to the usual rotations. And let me explain that. So I write here there are exactly phi of n explicit unique solutions up to rotations. Phi of n is an elementary function from number theory. It's the Euler-Totient function, which gives you the number of integers below n that are relatively prime to n, which means that their common divisor, greatest common divisor with n, is 1. So we know exactly how many there are. And there are some examples, and all these pictures here are not depicted with the actual mathematical thickness, because then these objects would be very thick, you wouldn't see much. But let me just, there's a nice popular account on that. We try to write it so that a more general audience can understand that. If you want to do some reading on this talk, just look at this one. Okay, so I would like to describe this construction for a particular example. Let's take n equals 6. We expect phi of 6 solutions, which are 2, because the number 5 and the number 1 are the only integers below 6 that are relatively prime to 6. And you see the solution already, or one of the solutions, with the actual thickness depicted. And now I would like to show you the construction, how it goes. So if you have n equals 6, you start out with 6 latitudinal circles stacked equidistantly on the surface of the sphere. And the property of these latitudinals is that they have actually the same thickness that is given. The thickness given is sine of pi over 2 times 6, so sine of pi over 12. And now you cut this sphere into 2 hemispheres, an eastern hemisphere and a western hemisphere, and rotate one hemisphere against the other. Thus, you disconnect first the curves and try to reconnect them in one single curve. And then Hendrik prepared a little movie, which I'm going to show here. So you start turning, and let me pause here. And already here you have one solution, because it's one connected curve. And by construction, it has the given minimum thickness. And the tube around this curve, the thick tube, covers all of the sphere. So you have a solution, because you cannot increase the length. You would increase the tube volume, but there's no volume left on the sphere. The sphere is covered already. If you turn further, you get something which looks appealing. So this is the actual thickness. And if you turn then further, you get something appealing. But this, for instance, is no solution, because there are too many components. Also, this is no solution. You have 3 components. Also, this is no solution. Only the last bit here gives you another solution, which is the mirror image of the first one. This is the second solution that you get.
Sorry, part of the definition of your problem is you wanted a connected curve?
Yes, just one connected curve. One longest rope. Yeah. Okay, so this is the explicit construction, and this fact that for these thicknesses you can really fill the sphere is the key point to proving uniqueness. Okay, you can also do this with open curves, and let me just show you some pictures of open curves that are the longest ropes with 2 ends on the sphere. And I only show that because it is a striking similarity to what we call Turing patterns on the sphere. So this is a completely different context. These Turing patterns appear from reaction diffusion equations as differences in concentrations. And the connection, the obvious connection that you look at remains to be investigated. I have no idea what this is about, but I would like to know what the connection is between our simple geometric variational problem and this PDE problem here. Okay, so now, having said that much about these thickness objects, I would like to follow 2 threads for this talk. One thread is, how can we relax these energies? So we have seen that we take a triple maximization of 1 over r, because that depends on 3 points. This is a non-smooth energy, and I would like to relax that maximization by some sort of other things. And the other thread is, how can we do that in higher dimensions? So higher dimensional objects in any codimensions is the ultimate goal. And to say that first, for thickness, we did it in one way, Pavel Steletsky and myself in 2004, and this is only one way of doing it, but let me explain that briefly. You take a 2-dimensional surface, let's say in R3, and instead of taking 3 points, you take just 2, but you demand a higher order contact. So now I'm looking for spheres that contain these 2 points, but that are also tangent to the surface at point x. So this looks like this. And the radius of that sphere, RTP, stands for tangent point radius, is also a multi-point function. It depends on 2 points on the surface and has a higher order contact here. And now we can do the same thing. We can look for the smallest such radius to define the thickness of the surface. And this is what we did. And there's a slight issue here because I said we always want non-smooth objects where these multi-point functions are defined on, and so the energies are defined on. But I demand a higher order contact here at the point x. That means I need a tangent plane at the point x. So that's why I wrote I infimize here over only good points where there is a tangent plane. And then you can ask, well, how smooth must the surface be to have a tangent plane at x? And for our purposes, it's completely enough to have tangent planes on a dense set. So it could be even a set of measure 0, a countable set, just it has to be dense. This is enough to define the thickness and to prove the corresponding theorems. So let me show you that theorem. First, the old one that we had for curves, and now the one for thick surfaces. And this is also an if and only if thing. If 1 over thickness as a geometric energy is finite, then you can say that sigma is a nice C11 manifold, submanifold of Rn or R3. So this is the topological control, and this regularity you have seen for curves before. It means that locally you can represent the surface as a graph of a function of exactly that regularity class. And remember, this is almost C2, so this has curvature almost everywhere in a sense. And this little word nice here in quotation marks means that we have additional control. So these graph patches describing the surface locally cannot get arbitrarily small. We have a lower bound on the patch size, which is a very strong control, and this lower bound only in terms of this energy. And this allows us to prove compactness for such surfaces. So you have a whole bunch of surfaces and say you have a uniform area bound, then you can prove that there's a subsequence of these surfaces converging nicely in that class again to a C11 manifold. And using that, we can prove the existence of ideal shapes also for surfaces. So these are so-called, well, I don't know your name, but this is the parallel to rope length minimizers, but now for surfaces. You minimize the quotient of area divided by thickness. The problem here is that this poses a lot of new open questions, because we can do this also for bounded surfaces. We can, for instance, ask, what is the shape of these minimizers? Certainly not like this. These are, well, soap bubbles, supposedly. If you dunk in this funny wire here with that shape into soap films, you either get something that doesn't even span all the boundary, or you proceed some holes. So if you do it in the classic way that minimal surface people did it with parametric minimal surfaces, you get a surface that has necessarily self-intersections, because that's the maximum principle. But our surfaces are different, because we prescribe a minimal thickness, and this means that we have embedded surfaces. And nobody knows what these surfaces look like yet. So there are many open questions about the ideal shapes. So, but let me now go back to that question, how can we relax these energies? And I write again this theorem, this old theorem on curves. And I stress the point that we have a very strong form of an energy here. You take a triple maximization over points. And what happens now if you replace this maximization or some of these maximizations by integrations, so by averaging? Do you lose a lot of control over this geometric object? And the answer is yes and no. You lose a lot of control, but you also keep a lot of control. So I only will talk about these energies that are completely relaxed. So all maximizations are replaced by integrations now. So these are geometric integrations over the curve, and there are three of them, because we have 3 arguments here. And this energy actually is taken for P above a critical case. And the critical case is the scale invariant case. See, if the scale, you see that 1 over r scales like a length, but you have 3 integrations that give you 3 times the length. So P equals 3 would be exactly the scale invariant case. All I'm going to say today is about the above the scale invariant case and integration. Okay, so the theorem reads as follows. If you have finite energy, and this is joint work with Marta Schumanska and Paul Strzelecki, then you can prove again that gamma is much nicer than before. It's not just a finite length curve, it is a C1 something submanifold, and this something actually tells you again something quantitatively about the derivative, about the tangent vector. So, in a sense, this is not only an arrow from up to down, relaxing the energy, but also from down to up, because you could now take, of this energy, you could take the power, you can take this to the power 1 over p. And if you have that, it's like the LP norm of 1 over r. And we know in mathematics that the LP norms of something converge to the L infinity norm, so essentially it's the primum norm as p goes to infinity. So this thing to the power 1 over p converges to this thing. So in that sense, we can see, if you take a formal limit here, that this kind of regularity converges to that kind of regularity. This is just a formal limit, but it says that this thing fits quite nicely into that image. Moreover, we can prove either by example or by some other things that this regularity in the classic function spaces is optimal. So you can either construct examples showing that, or you use later work by Simon Blatt, who is also here and who will give a talk on a different topic tomorrow, that you can turn this implication error into an if and only if statement if you replace these classic function spaces by fractional Sobolev spaces. So then you have a characterization of finite energy in terms of curves, in terms of these fractional Sobolev spaces that I'm not going into details about, but Philip Reiter might say something about these fractional Sobolev spaces later on. So this all fits nicely. Then there's the question, does this relaxed energy control more of the topology? And the answer is yes, and I will give you 3 example results. So we assume that we have a curve with finite energy for p greater than 3. This is formula 1. And then I say first, any inscribed polygon in the curve, inscribed polygon, whose edge length is controlled solely in terms of p and the energy value, is automatically isotopic to that curve of finite energy. Which means, in addition, that this energy bounds the so-called stick number of the knot. The stick number is the minimal amount of sticks you need to build a polygonal knot of the same knot class. So, since stick number bounds the number of possible knot types that can be represented by these stick numbers, means that we have a finiteness of isotopy for finite energy. In other words, if you give me a value E for an energy level or an energy barrier, I can say that there are only so and so many maximally and so many knot types that can be represented by curves with that finite energy or energy below that barrier. The second result concerns isotopy of nearby curves. And by nearby curves, I just measure this nearbyness in terms of Hausdorff distance, which in general is a very bad measure for saying anything about isotopy. So if you have a general knot in space and you give me an epsilon, then I can say within any epsilon neighborhood measured in this Hausdorff distance, which is a distance of sets, I can find arbitrary large types or arbitrary different types of knots. But if you have finite energy curves, gamma 1 and gamma 2, both satisfying this result, then this measure of sets is enough to say that these curves are automatically isotopic if this set distance is less or equal than that particular number. And the third result is a bound on the so-called average crossing number. So the average crossing number is something in the following way. If you have a knot in space, you can project it, for instance, to the ceiling. On the ceiling, you see something usually with self-intersections. It's a planar curve, and if it's a non-trivial knot, you get self-intersections. You can also project to this wall. You get another planar projection. Has again self-intersections, and you can count these self-intersections. And then you can look for the best projection, for the best direction, where you get the least amount of self-intersections. And they can do that for all kinds of representatives of a given knot class to find the so-called crossing number, which is an invariant of the knot type. The average crossing number for a certain curve does an averaging of these intersections. So you take all directions, you project in all directions, count at any time you count the number of intersections of the planar image, and then you take the average. This is the average crossing number, and by construction, the average crossing number is an upper bound for the crossing number of the knot type. That means if we control the average crossing number, we also control this not invariant crossing number. And we do with this inequality. For technical reason, it works only for this range of p greater than 12. No, so not for p greater than 3. This has a technical reason in the proof. And we get this kind of a bound. I should say this is not a very good bound, because this constant here, c of p, depends only on p, but it's very large. So this bound does not allow us, for instance, to say that our energy, this triple energy here, distinguishes between the knots and the unknots. So this means, do we know that the infimum over the unknots or all knots is strictly smaller than the infimum over all non-trivial knotted curves? We can't take this from this inequality because this constant is way too large to say that. But at least this estimate reproduces a characteristic power 4/3. And I told you before that for p going to infinity, these LP norms, our knot energies, tend to 1/thickness. So to rope length in a sense. And for rope length, there is such an estimate going back to Buck and Simon in 1997 that measures or that estimates the average crossing number in terms of rope length to that particular power. So we regain at least the power. And the reason behind all these results is a kind of excluded volume constraint that I want to describe now. I'm not going into any proofs, but what is behind all the theorems for this integral Menger curvature, for this triple integral, is the following geometry. So once you know that the energy is finite, bounded by E, you have the following geometric situation. Take any 2 points, x and y, that are in a distance less than a scale d that depends only on E. So here's the number depends only on E. If you are below that scale, you can say that the curve around x and y, say in such a ball around x and y, is contained in this intersection of cones. So this actually restricts the curve to run in here. In addition, you can prove that if you intersect these cones perpendicularly with planes, then you get in the plane only one curve point in the intersection. So the curve doesn't go back and forth within these cones. And this happens on every scale smaller than d. So in a sense, these finite energy curves are equipped with a necklace of diamonds. We call these things diamonds because they have certain similarities with diamonds. And this gives you an excluded volume constraint because there is a neighborhood where there's no part of the curve again. The curve is restricted to this diamond area. This is a much weaker form of excluded volume constraint than we had before with a fixed tube, because we don't have a unique next point projections. We don't have normal disks that do not intersect in a certain radius, but we have this kind of excluded volume constraint, a weak excluded volume constraint, and this is the key point to all the theorems I showed you for this relaxed energy. So now I would like to show you what can we do in higher dimensions. This was the second plan for this talk. Let's look at a surface again. Surface, a 2D surface, say in a 3 if you want. In contrast to our definition of thickness, we take now 4 points on the surface. Remember, for curves, we took 3 points, and it was the circumradius of these 3 points. So now one is tempted to say, well, these 3 points span a simplex, a triangle, so a planar simplex, and these 4 points span a spatial simplex, a tetrahedron. Why not take the circumsphere radius of that tetrahedron? This is tempting, and actually that's the first we wanted to do. And if you think of sigma being a sphere, a round sphere, then you see that this radius, the circumsphere radius, is exactly the radius of sigma. It's constant. No matter what 4 points you take on the sphere, you get always the same radius. So it's very tempting to take that. But we wanted to take something that is smooth for any smooth surface. So the integrand that we want to integrate over later on should be bounded for smooth surfaces. And this is not the case for the circumsphere radius, interestingly. If you have surfaces that possess a nodal line, like the graph of the function x times y, then you can prove that the circumsphere radius in the denominator blows up. And this is not what we want. We want something finite for smooth surfaces. So we regularized this thing a bit. We looked at the formula for the circumsphere radius, and 1 over the circumsphere radius corresponds basically to such a thing where there is more singularity in the denominator, so more zeros in the denominator that come from cancellations. So we erase these cancellations, and the simplest form that we came up with is a slightly more general or more regular integrand. We call that kappa of the tetrahedron, which is a kind of discrete curvature. So this is the version of Menger curvature for higher dimensions. In this case, for two-dimensional things. And with that at hand, we can prove the same theorem. Now we take two-dimensional sets, so they can be quite non-smooth. We just need some sort of connectivity. For simplicity, I wrote here that this is a Lipschitz surface, so it has a graph representation with Lipschitz functions, but you can be much weaker. You are above the scale invariant case. That would be 8 in this case, because we have 4 points here. These are all surface points. That means we have 4 integrations over the surface, and each integration is two-dimensional. So p equals 8 would be exactly the scale invariant case. If we are above that, we get again the same statement. We have a very nice C1 manifold with exactly the optimal exponent here. And we also say this is nice because we can control the graph patch size from below, just in terms of the energy value. And then we later on generalize this to arbitrary dimension and codimension, taking first the tangent point radius. And the Slavek Kolaczynski, who at that time was a PhD student of Pavel, then looked at the integral Menger curvature for arbitrary k-dimensional sets with a certain degree of connectivity. So say Lipschitz manifolds is certainly good enough. You take p above the scale invariant case. You take a simplex. This is k-dimensional, a k plus 1 dimensional simplex spanned by k plus 2 points. So that means you need k plus 2 integrations here. You take the same kind of discrete curvature, volume of the tetrahedron divided by the diameter to the power dimension plus 2, and then you get again the same statement. And in the meantime, Kolaczynski and Blatt have also made this to an if and only if, again by means of fractional Sobolev spaces. So we have a very clear picture. And this control that the graph patch size from the below is controlled gives you again the same type of topological consequences. So we can prove the existence of ideal shapes, ideal in quotation marks, because now this constraint or this minimization of that energy doesn't lead to thickness because it's just a weak form, but we can prescribe the isotopic class because it ensures embeddedness of the surfaces. So we could minimize area divided by this energy or something. Multiplied by this energy, which corresponds to area divided by thickness in the case p equals to infinity. And in addition, since we have nice control over the patch size, we also have a finiteness theorem for isotopy types. If you have a bound on the Menger, integral Menger curvature, we know, and in addition an area bound, so that things doesn't simply blow up, we can say there can be only finitely many isotopy types in these knotted surfaces, in these knotted submanifolds, that can be represented by a particular submanifold with that energy bound. So this can be compared to corresponding theorems from Riemannian geometry, where people like Cheeger or Anderson looked at sets of surfaces of submanifolds with bounds on the classic curvature. For instance, Ricci curvature bounded from above, and they needed bounds on the injectivity radius from below, and some area bounds. So let me say at the end, towards the end, that we have a lot of open problems, and I just want to mention 3 of them. The regularity of minimizers for these relaxed energies is quite open. We don't know anything, but we hope to show finally something, because that also could lead to some insight into the regularity of ideal knots, because this still seems to be not quite settled, this problem. So sending the regularity properties that we know for these p minimizers, sending p to infinity, we might gain some information. There's also some issue with so-called gamma convergence of functionals for p going to infinity. So there's some hope, but we don't know yet how to prove that. There will be a talk by Philip Reiter this morning about a similar energy where they can prove regularity of minimizers. What are the ideal shapes? I said it before, for thick surfaces we don't know anything, and we don't know, of course, anything about these minimizers, about the actual shape. And the last thing that is quite open is, can we flow to these ideal shapes? And flowing these relaxed energies is quite hard. And we see in the talk of Simon Blatt tomorrow how to do that with repulsive potentials, but this is a different story, and there might be some hope to do that. regarding this last point, there is a numerical gradient flow that was introduced by Tobias Hermes, at that time my PhD student. He wrote down an exact formula for the first variation of integral Menger curvature, which is kind of a mess. I wouldn't show you the formula. And then he discretized in space and time, and there's a nicely working algorithm that can flow these things. So this first example is flowing quite fast. You hardly see anything, so I won't start it before I say something. P equals infinity is almost P equals 50 is almost P equals infinity, in a sense. Because you will see that this final shape that you see here already is at least optically pretty close to the ideal trefoil. And the movement is quite quick, so this flow tries to embed this curve as nicely as possible. So this remains to be investigated, also experimentally, how large P has to be how close to the ideal knot shape. But for P equals 3, or a bit over 3, there you see that more the smoothing effects take place, like a curvature energy. It still preserves the knot class, but it's more a smoothed out object, and it's not so much the purpose of embedding it nicely. So if we had flows, if we had a hand on flows analytically or numerically for higher dimensional objects, you could solve the following nice problem taken out of the book of Morris Hirsch on differential topology. He asked the questions, do these seemingly very different objects, are they isotopic? And if you ask that question this way, the answer is probably yes, but why? You would put it into the computer, and the computer could flow it so that you can compare. But up to then, till we have that numerical gradient flow, you have to draw pictures, and with that picture I would like to close. Thanks very much.
So unfortunately, I missed a bit of it for reasons that won't go mentioned, but I'm wondering, what's the connection with the stuff like Tatiana Toro was doing with second fundamental form in L2 or LP or something like that?
Well, the connection is, on one hand, they worked to control the so-called beta numbers, which is a measure of how well the surface can be approximated by planes. To control these beta numbers is a big deal, also in this paper on the L2 norm of the second fundamental form. And if you have control, so that on the scale R, this beta number goes to 0 like R to some power, then you have C1 alpha, like this. And this is actually what we prove by hand, using our energies. We actually work to control these beta numbers. In a sense, the L2 norm of second fundamental form doesn't see self-intersections. So that's a big difference. And these energies here have these global and local effects. And I often get a very similar question, because these energies are so general that you can plug in even objects from geometric measure theory, so varifolds. You can plug this in, and then one compares these results, for instance, with theorems of Allard, regularity theorem of Allard. And somehow one has to really pay attention. They have a condition on the first variation. So this generalized mean curvature they have has to be controlled somewhat. And this condition actually is also a condition on the topology of these varifolds. So there cannot be too many holes. And this has to do with our assumptions on what surfaces we can plug in. So we need some sort of connectivity. So there can be a lot of dirt in the surfaces, a lot of corners, but we need some sort of connectivity somewhere to start our business.
So, not being directly in this field, this Menger curvature is sort of a discrete way of creating an integral of the curvature on some curve or surface in space in a discrete way.
It's a very weak form of curvature, yes.
Yes.
If you look at these theorems, maybe for curves, the simplest theorem, let me just scroll back to the very beginning, when we had this very first theorem. No, maybe not this one. Maybe the integral theorem is clearer. Then you see that as a kind of this lower theorem. You can see that as a geometric Sobolev embedding, actually. So what you have here is an integration over a three-dimensional domain. And this here is something like a weak form of curvature. So a weak form of curvature is something like second derivatives, very, very likely, only to the power p. And you know that if you have second derivatives integrated over a three-dimensional domain to the power p finite, then you get the Sobolev embedding. Exactly in the C1 alpha space with alpha equal that constant. So in a sense, you're right, this is a weak form of curvature control. But it also contains this global effect. So it tells you the thing is embedded. That's the additional feature, because it's a multipoint function in contrast to classic curvatures.
Could you just show the power law you had for average crossing number again?
Yes. The last thing.
Okay, so e to the 1 over p minus 3 is the thing that scales like length.
Yeah, I mean, you have to keep in mind that e is the value for that thing. If you take this to the power 1 over p and then send p to infinity, you get the right limit to 1 over thickness or rope length. Yeah? This is the point, yeah. So you have to take this to the power 1 over p to really have that convergence. But then you get this 4/3.
And if you took your stick number bound at the top and just said average crossing number of any polygon is certainly bounded by the square of the stick number,
Okay, I have
then
to.
you get something that's valid for smaller p, but you'd have the constant 2 instead of 4/3.
Yeah, maybe that's a good idea. I should look at this. Yeah, thanks.
Okay, so we should move on, but I can't resist asking, when you say you don't know anything about the minimizers for surfaces, even for surfaces, you don't even know that the genus 0 thing is a sphere? Or?
This we know. This is the only thing we know.
Okay.
The genus 0 minimizer for this thickness thing is the sphere. But we are very ashamed that we don't know that the minimizer of that energy is the circle. I mean, everybody believes that this must be the circle, and the numerics show that, but we can't prove it yet. This is a shame, but we can't prove it yet. We know that the circle is a critical point by the work of Helmholtz,
Sure.
but we don't know yet that this is the minimizer. We hopefully soon know.
Oh, that's interesting. Okay, well, we can talk more with our speaker at coffee, but we should start setting up for the next talk.